Hello and welcome to the Maths 2 component of the online degree program on data science. In this video we are going to talk about the notion of lengths and angles. So some of this may have already been seen in Maths 1 in some form, and some of this may be really easy and something you have seen before, but let's recall quickly what is the notion of lengths and angles. Okay, so let's talk about the dot product of two vectors in R2. So consider the vectors, let's start with an example. So consider the two vectors 3, 4 and 2, 7 in R2. So the dot product of these two vectors gives us a scalar as follows. Scalar is a real number. So you have 3, 4 dot with 2, 7. This is, so you take the first components of each of these vectors, multiply them. You take the second components of each of these vectors, multiply them and you add them. So this is going to give you 3 times 2 plus 4 times 7. So this is 6 plus 28, which is 34. Okay, let's generalize this to any two vectors in R2. So if you have x1 y1 and x2 y2 in R2, the dot product of these two vectors is the scalar or real number computed as follows. x1 y1 dot x2 y2 is x1 times x2 plus y1 times y2. So you multiply the first components, you multiply the second components and then you add those. Okay, so let's now ask what is the length of a vector in R2. So let's consider 3, 4, which we saw in the previous example while computing dot products. So if you want to compute the length of this vector, what do we do? Well, we use the Pythagoras theorem. So you drop a perpendicular down to, let's say, the x axis. So then if you do that, you get a right angle triangle. So using this right angle triangle, so this is a right angle triangle, and because this is a right angle triangle and since you have dropped a perpendicular, this length here is 3, this length here is 4, this is the x coordinate, this part is the y coordinate and so if you want to compute the length of the red line, that is the length of the vector, you use Pythagoras theorem, which says that the length of the vector 3, 4 is square root of, so the hypotenuse square is equal to the sum of the squares of the sides, that is the Pythagoras theorem. So the length of the hypotenuse is square root of the sum of the squares of the sides. So in this case it is square root of 3 squared plus 4 squared, square root of 9 plus 16, which is 25. So square root of 25 is 5, and we do not know here what units we are doing it in. So whatever units we are doing it in. So if this 1 is corresponding to centimeters, it is in centimeters. If 1 is corresponding to a kilometer, it is in kilometers. If 1 is corresponding to miles, it is in miles, and so on. Right. So whatever units are being used for drawing this R2. So the units is not important as far as this course is concerned. Of course, if you start doing physics and so on, then it matters, or if you do real life problems, it matters. Okay. So the main point here is that you have to remember that this, if you do a general x y, maybe we can do it right here. If I have x comma y, so if I have something like this, if you drop a perpendicular here, this is exactly x and this part is exactly y. So it gives you a right angle triangle, and so the length of this vector, if I call this vector v, so v, which is x comma y, its length is square root of x squared plus y squared. So this is really what we are saying here, right? Okay, so observe that, let's link this up with dot products. Observe that 3, 4 dot 3, 4 is 3 squared plus 4 squared, which we saw was exactly what was under in the square root part when we computed length. So the length of 3, 4 is the square root of the dot product of the vector with itself. So the length of the vector 3, 4 is square root of 3, 4 dot 3, 4, which is square root of 3 squared plus 4 squared, which is this is unfortunately wrong. This is root of 25, which is 5. Okay. So in general, of course, this is what I just said. The length of the vector is root of x squared plus y squared, which is exactly what you get by doing root of x comma y dot with x comma y. Okay, and here, as I said, this should be root 25 is 5. So the length of the vector is given by taking square root of the dot product with itself. Okay, this is the take home. So the length and the dot product are related in a very intimate fashion. Fine. Let us look at the angle now. So the other thing we want to study in this video is angles. So the angle between two vectors u and v. So this is a measure of sorry, this is not, there is no and here. The angle between the vectors u and v measures how far the direction is of v from u. Okay. So if you have the angle, this will be a small angle as compared to this, which is a large angle, right. So in our previous picture so there is a picture coming up. So we have our old friend 3, 4 and we have another vector 1, 5. So the angle is this thing theta here. So it measures how far in terms of directions these two vectors are from each other. So how far the directions of these vectors are from each other. Okay. Now we have seen this idea of directions and lengths which we called magnitudes in our very first video on vectors. So just recall that if you do not remember. So the angle is measured in degrees or radians. So if it is in degrees, it is between 0 and 360. So 0 is itself, and as you increase and go up to 360, it comes all the way back, and then 360 is again itself. So this is like a clock, right. If you have 9 AM and 9 PM, the clock shows you the same thing, but 12 hours have elapsed. So that is what this 360 is saying. If 360 means you have taken a round and come back, yeah. But as far as the angle is concerned, it is 360 and 0 are telling you the same things. Okay. Or it can be measured in terms of radians. So radians is more of a, it has something to do with the length of the arc. So that is measured between 0 and 2 pi. So again 0 is like this, meaning they are the same, and 2 pi is when you go all around and come back, yeah. So just pi, which is 2 pi by 2, so half of 2 pi is where they are like this. So the two vectors are parallel to each other but pointing in different directions, okay. Like from the center of the earth, the north pole and the south pole, they are in different directions, okay. So it is measured in degrees or radians. So this also tells you what is the relationship between degrees and radians, because 2 pi radians is equal to 360 degrees, okay. So from there you can say in general, if you have an angle of theta degrees, what should be the corresponding radians. Fine. The angle is often described by computing, or measured, maybe we should say, by computing its trigonometric functions. Described, or I want to say, or measured by computing its trigonometric functions. So which is sine, cosine, tan, etc. What is the relation between dot product and angles? So if you have two vectors in R2, we can compute the angle between which let us call it theta, between the two vectors by using dot products, as cosine of theta is u dot v divided by square root of v dot v times u dot u. So this times is these are real numbers, remember. So this is just multiplication in real numbers. So and then you can take the inverse cosine, and we usually think of it as being between 0 and 2 pi again. So let us do an example. So consider the two vectors. So this is in R3. So now we are talking about R3. So consider the two vectors 1, 2, 3 and 2, 0, 1 in R3. So the dot product of these two vectors gives us a scalar as follows. So 1 2 3 dot with 2 0 1 is you take component wise multiplication and then you add them. So 1 times 2 plus 2 times 0 plus 3 times 1, which is 2 plus 0 plus 3, which is 5. So for two general vectors, you do the same thing, x1 y1 z1 x2 y2 z2, you do x1 y1 z1 dot x2 y2 z2 is x1 x2 plus y1 y2 plus z1 z2. So now let's find the length of the vector, let's say 4 3 3 in R3. So to do this, we will first draw the xyz plane. So let's say this is x, y and this z. This is our right handed coordinate system. Oops, sorry, this is not y, this is y and that is z. So now if you take x y z, you drop a perpendicular. So this is 4 3 3. So you drop a perpendicular down to the xy plane, then join that to the origin, and then drop further perpendiculars from this point to the x axis and the y axis respectively. So what you really have is that this is a perpendicular, this is exactly z. So in this case it is 3, this is 3, and then this is exactly the length of y, which is again 3, the y coordinate, and this is 4, yeah, or this, because this is parallel to this, which is 4, this is parallel to this, which is 3, and this is parallel to this, which is 3. So now how do I compute the length? Again you use Pythagoras theorem. We already know that this line in the middle here, this line you can compute by Pythagoras theorem as square root of 3 squared plus 4 squared. So this is root of 5 squared, which is 5, and then again this is a right angle triangle, the green thing, the blue line and the red vector itself. So the red, blue and green form a right angle triangle, and the red is the hypotenuse, which is exactly the length of the vector 4 3 3. So length of 4 3 3 is root of 5 squared, which is the length of the line circled by the green line, plus 3 squared, which is the length of the blue line. But 5 squared I can write as 3 squared plus 4 squared, which was the original x and y coordinate. So this is 3 squared plus 4 squared plus 3 squared, or maybe we should write it as 4 squared plus 3 squared to keep with the notation, and then you can compute what that is. In this case it gives you root 34 units. So 16 plus 9 plus 9. So observe again that 433 dot 433 is exactly 4 squared plus 3 squared plus 3 squared. So the length of 433 can be expressed as the square root of the dot product of the vector with itself. This is the same computation, and so the general situation is where you do x y z, and the same reasoning tells you that the length of x y z is square root of the dot product of x y z with itself. So this tells you the relationship between dot products and lengths. So we have seen the same relation in R2, we have seen this in R3, and certainly the idea is that this holds for any Rn. The proof is the same. Let us now ask for what happens to the angle. So the angle between two vectors u and v in R3 is the angle between them computed by passing a plane through them. So if you have two vectors u and v, you look at, there is a unique plane passing through those two vectors, draw that plane, and now once you are on the plane, it is like you are on R2, and in R2 we know how to compute the angle between two vectors. And so what does this angle do? It measures the direction, how far the direction is of v from u or u from v on that plane. Okay. So we have seen this formula before in R2, and the same idea holds for R3. So if u and v are two vectors in R3, we can compute the angle theta between these vectors by using the dot product as follows. So cosine of theta is u dot v divided by square root of v dot v times u dot u. or you can write theta in terms of the inverse cosine of this number that we have just seen. So, let's maybe try to analyze why this is happening. So, the reason this is happening is because so if you have two vectors, so you pass some plane through them, I mean there is a unique plane. So, you take this plane, and now on this plane these vectors are like two ordinary vectors in R2. So, if you want, instead of looking at this plane, you move this plane, rotate it so that it becomes like the xy plane, and do not disturb those vectors, right. When you just do a rotation, do not do any scaling or anything else, yeah, just do a rotation. So, then these vectors are going to look like on the xy plane, they will maybe look like this, and you can compute the angle between them, and that is exactly what this angle is, and you can see that this will match with the formula that you have written down. Okay, that is the idea. Okay, so let us compute the angle theta between these two vectors 1 0 0 and 1 0 1. If our intuition is correct, we kind of know what the angle here is. Both of these are on the plane, the xz plane, right, y is 0. So, xz plane. So, these are on the xz plane, and on the xz plane, so you just knock out the y coordinate. So, on the xz plane, this is like 1 0 and 0 and 1 1. Okay. So, it is 1 0 and 1 1. So, if you think of the xz plane now as the xy plane, this is 1 0 and 1 1, and we know how much the angle is, right. This angle is exactly 45 degrees or pi by 4 radians, whichever you prefer. So, let us see if the answer that we get by doing that computation is the same. 100.101 is 1, 101.101 is 2, 100.100 is 1, and so we get theta is cosine inverse of 1 by root of 2 times 1, which is root 2, which is, as we know, is pi by 4 radians or 45 degrees. So, this last thing is something we are getting from a cosine table. You can look those up. Okay. So, let us look at this second example, the angle between 100 and 111. So, for 100 and 111, let us compute these numbers. 100.111 is 1, 111.111 is 3, which is what is giving that root 3, and 100.100 is 1. So, we get cosine inverse. So, theta, which is the angle between the two, is cosine inverse of 1 by square root of 1 times 3, which is cosine inverse of 1 by root 3, and you can look up a table to get what the exact value is. It is something like 54 degrees odd, if I remember right. Okay. And now we can do the general idea of make the general definition, that is, if you have two vectors u and v in Rn, the dot product is defined as component wise multiplication and then addition. So, u1 v1 plus u2 v2 plus un vn. The length of the vector is it is denoted by this 2 bars. So, it is called a norm, which we are going to study in the next video. So, it is given by root of u dot product with itself, and the angle between two vectors, again you pass a plane through those two vectors. There is a unique plane passing, and you can then rotate it so that it becomes parallel, it becomes the xy plane, and then you can measure, and it turns out that this is exactly the same as doing cosine theta is u dot v divided by norm of u times norm of v, which in other words is square root of v dot v times square root of u dot u, and then you can write it in terms of the inverse. Okay. So, we actually have seen a little bit of this before, lengths and angles, in our video on vectors, but this is a reminder, and it also is a reminder about what are dot products and how they help in computing the lengths and angles between vectors. Thank you.